Hello, this is Lab 2, Lines of Charge. Similar to Lab 1, the purpose of this experiment is to determine the amount of excess charge on a charged piece of tape. However, in this lab, I create a more sophisticated and accurate model for this charge by treating the charged tape as a line of charge rather than a point charge as seen in the previous lab. For this lab, I use the same experimental data from Lab 1, but will be creating a more advanced computational model. This lab is based on these physics principles. The law of attraction allowed me to determine if the tape was positively or negatively charged. Because I created a floating system in which the system was at equilibrium, I could use Newton's second law in conjunction with Coulomb's law to calculate the electric field and charge of tape B. For my following calculations, I had to make several assumptions. I assumed that each charged tape had the same amount of charge and that the charge was uniformly distributed across the tape, and the forces due to air resistance are negligible. In the experiment, I created two charged pieces of tape. Then I determined the charge of the tapes, which I found to be positive. Next, I arranged the tapes as seen in the diagram on the right. I brought tape A close to tape B until tape B started to float. By arranging them this way, I could use Newton's second law and the fact that the system is in equilibrium to determine the charge of tape B. This is evident in the force body diagram on the right. I also have here the important observations from my experiment, like the tape length, mass, and the distance from tape A at which tape B began to flow. On this slide, I show how I used Newton's second law and Coulomb's law to derive an equation for the charge of tape B. Because the net force is zero, the magnitude of the gravitational force is equal to the magnitude of the electric force. This is how I determined the charge in Lab 1. In Lab 1, I found the charge to be 1.24 times 10 to the negative 8 coulombs. To start my code for my computational model, I will assume the charge is the same. For my code, I started by defining the mass and charge of the tape. I initially used my charge from Lab 1, but then adjusted it until the magnitudes of the electric force and gravitational force were equal. I found the estimated net charge of the tape, when treated as a line of charge, to be 2.874779 times 10 to the negative 8 coulombs. These next lines were to define a function for determining the electric field. Then I used these two lines to define the two tapes. I input the distance between them and the tape length in the appropriate vectors. This section of code works to calculate the electric field and the electric force of tape B, the top tape. That's this section of code. The last section calculates and defines the arrows regarding the net electric force and the gravitational force. This is what my computational model looks like. In conclusion, if I modeled my tapes as single point charges, I would have found the charge to be the same as my earlier calculations, 1.24 times 10 to the negative 8 coulombs. This is less than the charge I got with my line charge model, which I found to be 2.85 times 10 to the negative 8 coulombs. These estimates differ because a distributed charge behaves differently from a concentrated charge at a singular point. The line charge estimate is likely more accurate because a charged piece of tape does not in reality have all its charge located at a singular point.